Hi students, in last class we discussed about Newton's universal law of gravitation. Now we will continue that class. In this class we will discuss about free fall and free fall acceleration. First of all, we will solve some problems based on Newton's universal law of gravitation. Problems. Calculate the force of gravitation between the earth and the sun given that the mass of the earth is 6 into 10 power 24 kilograms and mass of the sun is 2 into 10 power 30 kilograms. The average distance between the two is 1.5 into 10 power 11 meters. What are the given data? Now we will see the solution. Given that mass of the earth, already you know, mass of the earth is 6 into 10 power 24 kilograms. Remember this value, mass of the earth is 6 into 10 power 24 kilograms. And mass of the sun is 2 into 10 power 30 kilograms. Mass of the sun is 2 into 10 power 30 kilograms. The distance between earth and sun is 1.5 into 10 power 11 meters. You can represent this distance with D or R. You know the formula for gravitational force of attraction, that is F gravitational is equal G m1 m2 by r square. Here m1 is the mass of the sun and m2 is the mass of the earth. By substituting the values, we will get gravitational force of attraction is equal G value is 6.67 into 10 power minus 11 and mass of the sun is 2 into 10 power 30. Mass of the earth is 6 into 10 power 24 kilograms. And distance between sun and earth is 1.5 into 10 power 11. Here whole square is there, r square is there. So if you observe the 10 powers in numerator, 10 power minus 11, 10 power 30, 10 power 24. 10 power 30, 10 power 24 will become 10 power 54. If you subtract 11 from this, we will get 10 power 43. So 6.67 into 2 into 6 is equal to 12. So what we will get? 6.67 into 2 into 6, 12. Already we got 10 power 43. 1.5 whole square is equal 2.25. 10 power 11 whole square is equal 10 power 22. Force is equal 6.67 into 12 by 2.25 is equal to the 35.57. And 10 power 43 by 10 power 22 is equal 10 power 21 newtons. 35.57 into 10 power 21 newtons can be written as 3.557, nearly equal to 3.56 into 10 power 22 newtons. Two spherical balls of mass 10 kilograms each are placed with their centers 50 meters apart. Find the gravitational force of attraction between them. Here two spherical balls are there. Mass of each ball is 10 kilograms. They are placed with their centers 50 meters apart. The distance between the spherical balls is 50 meters. Find the gravitational force of attraction between them. So we will see the solution. First ball mass is 10 kilograms. Second ball mass also M2 also 10 kilograms. Distance between them, R is 50 meters. G value already you know, 6.67 into 10 power minus 11 Newton meter square per kilogram square. Gravitational force of attraction is given by, already you know the formula, F gravitational is equal G m1 m2 by R square. Here m1 m2 are the mass of the spherical balls. So by substituting the values, gravitational force of attraction is equal 6.67 into 10 power minus 11. This is G value. M1 is equal 10 and M2 is equal 10 by R is equal 50 whole square. That is equal to the each zeros from 10 and zeros from 50 square will be cancelled. In denominator, 5 into 5 is equal 25. 6.67 into 10 power minus 11 by 25. That is equal 6.67 by 25 is equal 0.2668. You will get 0.2668 into 10 power minus 11 newtons. 0.2668 into 10 power minus 11 newtons can be written as 2.668 into 10 power minus 12 newtons. This is the gravitational force of attraction between the two balls. Now we will see one activity. Place a small paper on a book. Take one small piece of paper and place that on a book. Release the book with paper from certain higher from the ground. Release the book with paper from certain height from the ground. The book and paper will fall on the ground at same time. Book and paper will fall on the ground at same time. We will observe that book, paper, they will fall on the ground at same time. Here we can see our physics textbook and small piece of paper. If the paper is kept in the book and released, then the paper will be separated from the book and falls on the ground little bit later than the book. If the paper is kept in the book and released, then we will observe that the paper will be separated from the book and falls on the ground. Both will falls on the ground little bit later than the book. Here paper will reach the ground little bit later than the book. What is our conclusion? Book and paper are having different masses, but free fall does not depends on the mass. There is a little bit difference. That is due to the air resistance. If there is no air resistance, book and paper will reach the ground simultaneously. A body is said to be in free fall when only the gravitational force acts on the body. When a body is falling towards the earth, if only gravitational force acts on that body, then that body is said to be free fall. A body is said to be in free fall when only the gravitational force acts on that body. Let us drop a body of mass m near the earth's surface. Take one body of mass m. Let drop that body near the earth's surface. Let capital M be the mass of the earth and R be the radius of the earth. Here capital M is the mass of the earth and capital R is the radius of the earth. Small m is the mass of the body. Here we can see apple. Mass of the apple is small m. Mass of the earth is capital M and radius of the earth is capital R. Now the force of attraction on the mass is given by, already you know the formula for force of attraction between two bodies. That is equal to the F is equal GMM by R square. Here M is the, capital M is the mass of the earth and small m is the mass of the object. If you transport small m to the left side, F by m is equal Gm by R square. We will get F by m is equal Gm by R square. From Newton's second law, already you know, from Newton's second law, F is equal ma, or F by m is equal to the acceleration. F by m is equal acceleration. Here this acceleration is denoted by g. In place of small a, we will write small g. This is free fall acceleration. So what we will get? G is equal Gm by R square. In place of F by m, we are substituting small g. Small g is the free fall acceleration. So what is the formula for small g? Free fall acceleration small g is equal Gm by R square. G is the universal gravitational constant and m is the mass of the earth. R is the radius of the earth. So what we can say from the above equation, we can conclude that small g is independent of mass of body. In the formula of small g, there is no mass of body, small m. Small g is equal Gm by R square. There is no small m. That's why we can say that small g is independent of mass of the body. It depends on the mass of the earth and it depends on the distance of the object from the center of the earth. Small g depends on the distance of the object from the center of the earth. If there were no air friction or resistance, all the bodies would fall with same acceleration. Small g does not depend on mass of body. You can take higher mass object and lower mass object. If there were no air friction or resistance, all the bodies would fall with same acceleration. All the bodies will fall with same acceleration. This acceleration produced due to the gravitational force of the earth's surface is called free fall acceleration. This acceleration produced due to the gravitational force of the earth's surface. Already you know, earth has gravitational force of attraction towards all bodies. Due to that force of attraction, there is a acceleration, production of acceleration. This acceleration produced due to the gravitational force of the earth's surface is called free fall acceleration or acceleration due to gravity. Free fall acceleration also called as acceleration due to gravity. The body having a free fall is called freely falling body. The body having a free fall is called freely falling body. Galileo proved that acceleration of an object falling freely towards the earth does not depend on the mass of the object. Galileo proved that acceleration of an object falling freely towards the earth does not depend on the mass of the object. Already we discussed small g does not depend on the mass of the object. This was proved by Galileo Galilei. He also called as father of modern science. Galileo Galilei also called as father of modern science. Here we can imagine that vacuum is created by the evacuating the air from the glass jar. Here we are creating vacuum by evacuating, by removing the air from the glass jar. Here there is a glass jar. We are creating vacuum by removing air from the glass jar. Now we are taking one feather and one coin. By releasing feather and coin at a time from the glass jar, we will observe that they will reach at same time. They will reach the bottom of the glass jar simultaneously. The feather and the coin fall with same acceleration and reach the ground at the same time. This experiment was done by the Galileo Galilei from the Pisa Tower. So, finally he concluded that G value does not depend on mass of the object. G value does not depend on mass of the object. Small g is equal gm by r square. Already you know this formula. Acceleration due to gravity small g is given by gm by r square. Here g is the universal gravitational constant and m is the mass of the earth. R is the radius of the earth. R is the radius of the earth surface. Mass of the earth is, already you know the value of mass of the earth, that is 6 into 10 power 24 kilograms. Mass of the earth is 6 into 10 power 24 kilograms. Radius of the earth is 6371 kilometers or 6.4 into 10 power 6 meters. Radius of the earth is 6371 kilometers or 6.4 into 10 power 6 meters. Remember these values. By substituting these values, putting these values in the above equation, we will get small g is equal 9.81 meter per second square or 981 centimeter per second square. By substituting the values, we will get small g is equal 9.81 meter per second square or 981 centimeter per second square. Remember the small g value also. This is also very important. This value changes due to change in distance of the object from the center of the earth. Small g is inversely proportional to r square. Already you know the formula, small g is equal gm by r square. So we can say small g is inversely proportional to r square. If the distance of the object from the center of the earth will change, then small g value will change. Since free fall acceleration is constant near the ground. Since free fall acceleration is constant near the ground. Near the ground, r is constant. So, free fall acceleration also constant. The equations of uniform accelerated motion can be used for the case of free fall body. Already you know equations of uniform accelerated body. What are those? V is equal u plus at. V is equal u plus at. S is equal ut plus half at square. S is equal ut plus half at square. V square minus u square is equal to 2as. These are the equations of uniform accelerated motion. Once again, V is equal u plus at. S is equal ut plus half at square. V square minus u square is equal to 2as. Here what is u? U is the initial velocity. V is the final velocity. A is the acceleration. T is the time. And S is the distance or displacement. While solving problems related to free fall objects, we use small g instead of a. Small a in above equation. Small a is the acceleration. Small g is the acceleration due to gravity. While solving problems related to free fall object, if we are solving problems related to free fall object, we will substitute small g in place of small a. By substituting, we will get v is equal u plus gt. v is equal u plus gt. S is equal ut plus of gt square. Is equal ut plus of gt square. V square minus u square is equal 2gs. These are the equations for the freely falling objects. These are the equations for the freely falling objects. When we use these equations, we must follow the sign convention. When we use these equations, we must follow the sign conventions. Now we will discuss about sign convention. Before going to discuss about sign convention, first of all, we will see the direction of the g. In which direction free fall acceleration will work. Throw a stone vertically up. Measure the time required for it to come back to the earth surface with stop clock. Take one stop clock. Take one stone. Throw a stone vertically upwards and measure the time required for it to come back to the earth surface by using stop clock. When the stone moved up, its velocity decreases gradually and finally it becomes 0 because it is moving against the direction of gravitation. You know, when the stone is moving upward direction, its velocity decreases. Why its velocity decreases? Because it is moving against the direction of gravitation. It is moving against the direction of the gravitational force of the earth. That's why its velocity slowly decreases and finally it becomes 0. When its velocity becomes 0, it starts to fall down. When its velocity becomes 0, again it returns back. It starts to fall down due to the gravitational force of the earth and its velocity increases. When it falling towards the earth, its velocity slowly increases. Why its velocity slowly increases? Because it is traveling in the direction of the gravitational force of the earth. So what is the direction of the g? G always acts toward the earth surface. When a stone moves up, the speed decreases. When a stone moves down, the speed increases. From this observation, we can say, so the free fall acceleration is vertically downwards. Free fall acceleration always acts toward the earth surface or always acts vertically downwards. No matter how you throw objects, g is directed vertically downwards. G is always acts vertically downwards. Have you thrown the objects? G always directed vertically downwards. Here we can see G always acts toward the earth surface or vertically downwards. Now we will see the equations of vertical motion. Equations of vertical motion. While the stone or object is moving up, the direction of acceleration is in upward direction, which is against to the direction of gravitational force. When the stone is moving up, the direction of acceleration of the stone is in upward direction. The direction of acceleration due to gravity is downward direction. The direction of acceleration is in upward direction. So this is against to the direction of the gravitational force. That's why A can be taken as minus G. When a body is thrown vertically upwards, the equations of motion are. Now we will see the equations of motion when a body is thrown vertically upwards. When it is thrown vertically upwards, there is a initial velocity. Initial velocity is the u. And final velocity. Final velocity is the v. Distance travelled by stone is the h. And acceleration due to gravity is negative because it is travelling opposite to the direction of the gravitational force or opposite to the direction of the g. So g is negative. Body is thrown upwards. U is there. U is the initial velocity and v is the final velocity. H is the height travelled by the stone. Here A is equal to the minus g because it travels opposite to the direction of the g, or it travels opposite to the gravitational force of the earth. That's why we are taking g as negative. By substituting these values in the equations of motion, we will get v is equal u minus gt. v is equal u minus gt. H is equal ut minus half gt square. H is equal ut minus half gt square. V square minus u square is equal minus 2gh. V square minus u square is equal minus 2gh. These are the equations of motions when a body is thrown vertically upwards. These are the equations of motion when a body is thrown vertically upwards. In this case, A is taken as plus g. Here we can see freely falling body. For a freely falling body, initial velocity u is 0. Remember, for a freely falling body, initial velocity u is 0. Slowly its velocity increasing. V is there, h is the height from which it is falling, and A is plus g. By substituting these values, we will get v is equal gt. v is equal gt. H is equal half gt square. H is equal half gt square. V square is equal 2gh. V square is equal 2gh. These are the equations of motions for a body thrown upwards. All of you prepare well, make notes. We will continue in next class. In next class, we will see the problems based on these equations. So, prepare well and make notes.